So my name is Michael Brett. I lead the applications team here at Rigetti. And so that means we're responsible for working very closely with customers, understanding use cases, developing out the applications that they're interested in and looking at performance around that. And so what we have for you this afternoon is quite a showcase of applications that have been developed on the Rigetti architecture, including some recent results out of the Aspen 7 chip that you saw a briefing on this morning. So we're quite excited to share with you some work that's been done internally at Rigetti, but then also many of our developer partners that have been working on these chips as well. So we've got quite a few to get through. It'll be fairly rapid fire looking at these applications. And so we'll sort of introduce everybody at once and then do questions afterwards. And then after the application session, Eric Kessler from AWS Bracket will be giving an overview of that platform and how it integrates with Rigetti, and we'll do a little bit of coordinated Q&A on the AWS Bracket platform before going to the break. So it's a great session. So the first four application groups, which I'll quickly introduce, we'll start with Marco Paini, who's internal at Rigetti and part of the applications team there. Then Ewan Monroe from Entropica, Ryan LaRose from Michigan State University, and Stallone Alves from Boxcat, giving an introduction to some of the work that they've been doing. So, Marco, over to you.
Thank you, Michael. Hi, everyone. So we've heard this morning the work that our colleagues are doing on the hardware, on the platform to get us closer to quantum advantage. And as application people, we also need to contribute to try to accelerate the journey to quantum advantage. And practically, what is it that we can do? So we can imagine business problems and their solutions and NISQ algorithms and their applicability as being distant for now. And we could start from business problems and apply today's algorithms and empirically, with iteration, try to improve the quantum solution. Or on the other hand, we could start from NISQ algorithms and try to improve the foundational algorithms. Today I'll talk about two examples, one in fact that starts from business problems and one that starts from trying to improve NISQ algorithms. With the work on the hardware and on the platform, the effort on both directions is hopefully what will help create an overlap between the two circles, an overlap which actually represents quantum advantage. Okay. So I'll start from the first case, which is starting from a business problem, or actually in this case, a business opportunity. And so the recent entry of small satellite players in the market resulted in the availability of images, satellite images that are cheaper, but with more available, but actually also of lower resolution. So this means that it's cheaper to access satellite images, but you need better machine learning tools to be able to make practical use of it. There are many use cases that can actually make use of these images, from commercial use cases, defense use cases, and even environmental. So you could be monitoring deforestation, for example. So we ask ourselves the question on how would today's known QML algorithms perform on this classification problem with these images. And we take one specific model. This is a model that was developed by a colleague about a year ago. It's called Quanvolutional Neural Network. What it means is fundamentally it introduces as a layer in a convolutional network a quantum circuit, which has the function of creating nonlinear random transformation, which by design is difficult to reproduce classically. Now, other than having to be difficult to reproduce classically to be possibly interesting, it also needs to produce a valid result. And so we verified this empirically, in fact, on a set of images, and this has been executed on the QPU. And so on the y-axis, we have the accuracy as a function of the training iterations. We still see that a convolutional network, which was used, a classical convolutional network, which was used as a benchmark, and it was designed in a way to be fundamentally a fair benchmark in terms of size and execution time as the convolutional, still does a little bit better than the last execution on the quantum network. It's interesting to observe, however, that compared to the original convolutional neural network model, the one that was originally designed a year ago, a series of empirical improvements that were added to the initial model meant that the results now improve and got close or somehow close to the classical results. So the takeaway, again, on an approach that starts from a real business problem on a real data set is with empirical ongoing improvements, how far can we actually get the result on the quantum system in terms of how close can we get it to the classical result. Yeah. So I'll move on now to the other case, which is a very different case because this starts from foundational algorithms. Yeah? And this structure, so the variational hybrid algorithm, Rigetti has been really focused on improving and doing platform level enhancements to optimize for these type of algorithms. There is, the way they work fundamentally, there is an internal loop, so the problem is that of finding the minimum of an objective function, which is expressed as the expectation value of an observable as a function of the parameter. And the way it works is you start with one given value of the parameters, you do a set of internal loops, and you determine that expectation value for that value of the parameters, and then the classical optimizer on the outside loop gives it another set of values. And again, the internal loop determines the expectation value for that, and the outside loop with an optimization determines and drives the parameters that are passed on to the internal one until the minimum is reached. Yeah? So again, we asked the question of what is it that at an algorithm or application level we can do or could do to do better. Now, I think one challenge, and it's a fairly obvious challenge on this, is the number of executions, because you've got a substantial number of shots of the internal loops that is then multiplied by typically another pretty significant number of outside iterations. And so overall, the number of execution can be very high. Additionally, there's another problem that is less obvious from this, which is the initial parameter isn't necessary, so the choice of the initial parameter isn't necessarily obvious. And so in fact, we have a decent probability of choosing an initial parameter, which puts us in a condition with that the minimization will be very difficult. And so ideally, one thing we would like to be able to do is something like this. Now, this we can't really do because by definition, the shots give you a value of the expectation value for one set of the parameters. And so to do something like this, we would have to modify it in a way that instead of giving you the expectation value for one set, you would have to have it for all sets of the parameters. Now, we can't do this with the shots as they are defined now, and so we would have to introduce a slightly different concept. And in fact, the concept we introduce is that of snapshots. And so a snapshot is fundamentally simply consists in rotating each qubit in a random direction and then measuring each qubit. And then that information is written down, and then another snapshot is done. And the information collected through the snapshots is such that that's sufficient to calculate the expectation value of any observable of the system, and therefore of any Hamiltonian or any observable as a function of parameters. So to prove this, we've actually executed on the QPU. And I'll just describe the ideal experiment, ideal in the sense that it actually proves this point about being able to calculate the expectation value of any observable. So we start from a random state. So random means, and it's a 12-qubit state. So random means we start from a 0-0 state, and then we do a few Hadamard and a few XY with random parameters to a few pairs of qubits. Yeah? And then we take the snapshots. And then, so the statement is, then we want to be able to show that given any observable, we can calculate the expectation value with some approximation. Yeah? And so we take 20 random observables, defined as 20 random Hermitian operators. And we calculate the absolute difference between the exact expectation value and the one calculated with the snapshots. So it's interesting that two things. One is, well, this graph, so the expectation is that the error on this calculation is a random normal variable that has standard deviation 1 over the square root of the number of snapshots. Yeah? And so in a way, the chart confirms the result, because we see that we get about 1 out of 20, so 5% at around 2 standard deviation, as you would expect of a normal variable, and about 6, 7 or so at 1 or more standard deviation, which is 1/3, again, as you would expect. The interesting thing is, though, that not only it confirms the theory, it actually seems to correspond to a result to a method that is quite insensitive to readout errors. So the method consists in single qubit rotation, which we would expect do not cause a lot of trouble, but then there's readout. And actually, the effect of readout or the readout errors is almost absent. And this is, in fact, because the distribution is qualitatively as you would expect if we were to simulate this. Yeah. So now, an algorithm, I think, is interesting if it has 2 features. So the first one is it's got to scale, because it's good that it worked for 12 qubits, but if we know in advance that there are certain things that go exponentially bad as you increase the number of qubits, then that's not particularly useful. The other thing is, of course, it's got to have some real-world application that it can be used for. So let's start from scaling. So scaling is relatively simple, or it scales efficiently in the sense that for every qubit added, only a single rotation, a measurement of that qubit is introduced. The error does not directly depend on the number of qubits. So from this perspective, we can increase the number of qubits, and all we would do is just simply add a random rotation and measure that additional qubit. Now, the error depends, however, on the size of the observable. Where actually, mathematically, the size is defined as a semi-norm in the space of the operators. Now, other than, again, the mathematical definition, what does this mathematical definition mean in practical terms? So, and to respond to that, I will look at 2 classes, two important classes of applications. We could consider optimizations too, combinatorial optimization, which are somehow for this somewhat easier, but I think simulation and quantum simulation and machine learning are particularly interesting. So for quantum simulation, in the worst case scenario, this size, so the semi-norm, grows just a bit more than linearly in the size of the problem. Therefore, it is of practical use for quantum. The method is of practical use for quantum simulation. The hope with this is that, of course, is to do fewer iterations or fewer executions to find the ground state. But also, given that you have the explicit dependence of the function on the parameters, is to be able to possibly do a better optimization. Now, there's some initial work that the UK MPL has started to do, extending some work that they've done on VQE on some solid-state physics model. And they have now applied this method to the smallest of their model, and they found the exact ground state, which is not surprising because it's a small model. And they found it with like a couple of hundred fewer iterations than you would do with VQE. Yeah. The other interesting case is quantum machine learning. And it is interesting because most variation of quantum machine learning consists in the optimization or the minimization of an objective function which contains the expectation value of projectors for the bit strings. Now, interestingly, the size, so the semi-norm, is more or less equal to 1 for any number of qubit, which means that this is another case where it can be applied for any number of qubit. And so there are a lot of interesting applications for this. One that we're looking into is generative modeling, and in particular, we're working on this with a client, which is a financial services client, and the use case is the generation of synthetic financial data. So working with client or with the business community or commercial organization in general is extremely important. And yes, we do want to work and create better NISQ algorithms, and we need the support of the research community to do that. But also, we want to start from real business problems. And the support and engagement of commercial organizations not only can help pinpoint to the right real world use cases, but in general can support the development and the growth of quantum computing as an industry. So I'd love to talk later or anytime in 2020 and beyond. Thank you.